Welcome back to the FE Exam Review Series, where we focus on problems built around core fundamentals that will help you pass your FE exam. Today's problem is based on the Thermodynamics Section D processes. I highly recommend you try the problem for yourself before you watch this video solution, and you can do that using the first link in the description below. I hope you tried the problem. Let's get into the solution. A gas mixture of 40% nitrogen and 60% helium by mass expands isentropically. So reading through those first couple of lines, what I see is that I'm given the mass fraction of nitrogen, it's 0.4, as well as the mass fraction of helium, it's equal to 0.6. And I have an isentropic process that's occurring. That means we have constant entropy, or the change in entropy is equal to 0. We're expanding isentropically in a turbine from 6,000 kPa and 700 degrees C. So I'm given my initial state, P1 equal to 6,000 kPa, and a temperature at state point 1 equal to 700 degrees C. I move through that turbine. I end up at a different state point, a pressure at state point 2 of 300 kPa. So I'm expanding in that turbine. I'm told to use room temperature properties and find what the work per unit mass is. Now, what we usually want to do when we're looking for work or heat transfer is we want to use the first law of thermodynamics. We're looking at a turbine in this case. And in a turbine, there's mass moving into and out of the system. What that means is we have an open system, and generally, the first law of thermodynamics states that the heat transfer minus the work is equal to the change in the energy of the system. But for an open system, we have the change in enthalpy plus the change in kinetic energy plus the change in potential energy that replaces that change in energy. Now, the difference between an open and closed system is just that instead of enthalpy here, we'd use internal energy. But we have an open system here, so it's enthalpy. Okay, if we go through and cross off some of the irrelevant terms, we know that we have an isentropic process. Isentropic means adiabatic and reversible. Adiabatic means zero value for the heat transfer. We're not given any speeds, so that means we can neglect kinetic energy changes. We're not given any heights, so that means we can neglect potential energy changes. That means that the work is equal to the change in the enthalpy, or if we divide both sides by the mass, the work per unit mass is equal to the change in the specific enthalpy. And you note that I just neglected that sign there because it doesn't matter. All of our choices are positive values, so I'm not going to really worry about the sign. I'm just going to look at that change in enthalpy value. Now, in order to find the change in enthalpy, how the enthalpy changes with temperature is contained by a property Cp. So if we wish to find the change in enthalpy, all we need to do is take Cp and multiply it by a delta T, that difference between T2 and T1. Now looking at our given properties here, we do have what a T1 value is, but we have no clue what the Cp of the mixture is, as well as no clue what the temperature at state point 2 is. We do know that the process is isentropic, and if you recall, for an isentropic process, there is a relationship between the pressure ratio and the temperature ratio. T2 over T1 is equal to P2 over P1 raised to the K minus 1 over K, where K is the ratio of specific heats. Now we're going to check in the reference manual for all of this this kind of information, but I'm just kind of showing you how intuitively we would go ahead and solve this problem. So we have that. We'd be able to find T2 because we know all this other information. What about Cp? So I'm giving you some intuition here for how we find properties, intensive properties of mixtures for ideal gases. If we were looking at the enthalpy of the mixture, we can sum the enthalpy of the first component and the enthalpy of the second component if we had a two-component mixture. If we look at the specific enthalpy, so we take the mass of the mixture multiplied by the specific enthalpy of that mixture, that's equal to the mass of the first component times the specific enthalpy of the first component plus the same thing for the second component. If we divide both sides by the total mass here, I'm seeing some ratios pop up. M1 over M, that's the component mass over the total mass. That is just the mass fraction that we were given. So we can use the mass fractions to be able to find intensive properties like CP or CV. Let's go inside of the reference manual and I'll show you where exactly you can find this information. This is in the thermodynamics section here, page 145. In the thermodynamics section for a constant entropy process, you could see that relationship we spoke about before, where the temperature ratio is related to the pressure ratio, using that ratio of specific heats, K. Additionally, looking at more information for ideal gas mixtures, what we see is that using the mass fraction, which is defined here, that Y value, we can find some other intensive properties. We can find CP of the mixture. We can find CV of the mixture. What is our plan in general? What we're going to do is that work per unit mass term, it's equal to CP multiplied by T2 minus T1. And we know something about T2. T2 is just T1 multiplied by the pressure ratio raised to the K minus 1 over K. If we go ahead and plug that in and make some substitutions, what we get is CP T1 multiplied by P2 over P1 raised to the K minus 1 over K. If we take that and subtract off 1, we have the work per unit mass. So we need CP of the mixture. We need K of the mixture, so we can do that using CP and CV and the mass fractions. And we know what T1 is, so we're pretty much ready to solve the problem. All we need to do is get some of that property information from the reference manual. We need to know CP and CV of nitrogen and helium. We're going to use those mass fractions to plug in everything into this equation here. Let's go ahead and grab those properties. Page 175 for me. So if you go ahead and check on page 168 of the reference manual, you can find at room temperature these properties for helium and nitrogen. You can see what CP of the mixture is for nitrogen and helium, as well as what CV of the mixture is for helium and nitrogen. Let's go ahead and compile that information back where we were doing the problem. We're going to take, to find CP, we're going to use that mass fraction of nitrogen multiplied by the CP of nitrogen. And we're going to add it to the mass fraction of helium times CP of helium. Are we going to find CV of the mixture? We're going to do the same process. So we have all the properties. I'm going to go ahead and plug in to get what these ratios, what the CP and CV is. I'm going to take their ratio to get K, and then I'm going to come back to the video. Okay, so right here you can see what I got for CP. It's 3.53. What I got for CP, 2.1692, and what I got for K, which is the ratio of the two. I'm going to go ahead and plug it into my main equation here and show you what the final output is in terms of the answer as well as plugging in the values. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from. And all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top 3 subjects, what are my bottom 3 subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $29.99. Let's get back into the video. After plugging in, what we ended up getting was negative 2352.35. And that negative sign is because up here you can see that what we ended up doing was neglecting that negative here. So it's actually a positive value. If we go ahead and check that answer here, 2352. Okay, so we did get the correct answer. Again, looking at that negative sign, what does a positive work essentially mean is we have work outputted from the system. That means the substance is doing work onto the surroundings, which means that we're kind of expanding, right? So that positive sign does make sense. In terms of what we did, we looked at the first law of thermodynamics. Once we looked at that, we concluded that the work per unit mass was just the Cp delta T. We weren't given any kinetic energy changes, so we didn't take that into account. For a constant entropy process, there was a relationship between the temperature and pressure ratio. So we used that to find T2, as well as fundamentally what we did was use the mass fractions to find Cp and Cv of the mixtures. And we kind of spoke about intuitively why that makes sense. We went ahead and found Cp and Cv. We also found K of the mixture by taking their ratios. We plugged it into our bulk equation, which is down here, and we ended up getting 2352 kilojoules per kilogram. If you enjoyed the video and you learned something, consider leaving a like and subscribing. Thanks for watching. I'll see you in the next video. Goodbye.